Okay, hello everyone. Here I want to explain to you about the last topic of the physics course that was about transformer. Okay, transformer is one of the most common applications in electromagnetism, as I've said on our previous meeting. Okay, Bismillah. And I guess I hope you have already watch the video about the transformer itself. So here I just want to review some materials about transformer. Okay, first, talking about the transformer itself. Transformer is a passive electrical device that transfers electricity energy between circuits through electromagnetic induction, primarily used to step up or step down voltage levels. Okay, here we have two types of transformer, which we know that in the transformer there are three elements. That was the first one is primary coil, and then the magnetic core, and then the last one is secondary coil. Okay, and this is step down transformer. When we know here that step down transformer itself, it's used to step down the voltage. Yeah, when we have a huge voltage in the primary coil, so we can decrease the value or the magnitude of the voltage on the secondary coil. Yeah, and then for the stepping up transformer, it work reversely. Yeah, so here in the primary coil we have a small amount of voltage. Then when we apply this small amount of voltage to this step up transformer, so we will have the result voltage will be higher, yeah, than the primary coil, like that. Okay. Okay, now we're talking about the component again. Okay, the first primary coil, which in quantity 1 we define the magnitude or the value of the primary coil as the turn of the coil itself. Yeah, so it's NP, turn of the coil, turn number of the coil. Okay. Secondary coil is NS, and the third one is magnetic core. Actually, for the transformer concept itself, we will apply the concept of electromagnetism, which we know that to create an EMF or electromotive force, it's equal to minus N d phi per dt, right? And as we know that this is Faraday's law. Okay, and EMF itself, we can also symbolize the EMF by epsilon like this, or define as a voltage. Okay, so we have this equation. But the question is, when we have two types of coil on the image above, yeah, and the coil, it has both has different turns number of the coil. Let's say that this is NS and this is NP. Yeah, for this example is type of step up transformer. Then we will also have Vs as the so sorry, it's reverse. Okay, first for the primary coil we have primary voltage, then primary turns. For the secondary one, it's secondary turns and secondary voltage, like this. Okay, and let's say that epsilon p is equal to VP, since we know that the epsilon, it represents a voltage number, so VP also equal to E epsilon P. Okay, so it goes the same for the Vs. Vs is equal to epsilon P, epsilon S, sorry. Okay, so because we have two circuits here that connected to a different device, let's say that for the left side, the primary coil is connected to a source of AC. It can be generator or something. Okay. Then for the right side, we will have secondary coil that connected to a device that we want to connect it to. Something like a lamp maybe, or some electronic device that needs to step up. Yeah, something like that. I guess for the electronic device is need the step down transformer. Yeah. Okay. Okay, let's say that we have two kinds of circuit over there. So we will have two different equation. Yeah, so the first one is epsilon P, which is represented the primary coil, is equal to minus NP the epsilon per dt. Okay, talking about the the phi per dt itself, because this is the change of the magnetic flux, yeah, per time. So we can actually remember first about the concept of the electromagnetism induced, yeah, induction. As we know that when there is a current, yeah, flowing through this wire, and there is a change in, let's say that there will be a change in the current itself, so it will induce a magnetic flux, yeah, inside this coil, and this magnetic flux will move to the other side, yeah, let's say that to this side. Yeah, I just give the arrow is just assumption. Okay, so the case will be different uh, based on the direction of the current. Okay, so this is just the assumption. Okay, when we have this magnetic flux, yeah, let's say that this is magnetic flux. The magnetic flux will be the same, yeah, both in the left side or in the right side. It will be the same. Yeah, so we just write the d phi per dt is the same as d phi per dt in the both side. So epsilon p is equal to this, and epsilon s is equal to minus ns d phi per dt as well. Okay, so from this equation, actually we can find the new equation that I want to write over here. We will find the transformer equations. Okay, so we will have epsilon p divided by epsilon s equals np divided by ns. And as we know that epsilon p, it represents the voltage number, so epsilon p can be replaced by Vp, or the voltage of P, and it goes the same for the secondary one. Yeah, so we have this. Okay, you got it? Okay, I hope you got it. Okay, and based on this transformer equation, we can also derive the the concept of power that dissipate or store in the both circuit. Yeah, let's say that it's a different circuit, yeah, the primary circuit and the secondary circuit. And for the primary circuit itself, yeah, let's say that we will have P P, yeah, or primary power. And on the right side, we will have PS, or secondary power. Okay, so in ideal transformer, yeah, we will hope, yeah, and we will also hope that every transformer has this type of transformer. That was ideal transformer. The ideal transformer itself will allow the power conservation. Okay, power conservation itself means that the PP will be equal to PS. And as we know, P in our previous meeting talking about direct current, I guess, we know that power is equal to voltage times current. So because this is the subscript is P for primary, so it's PPIP equals VSIS. Okay, so this is the case for the ideal transformer. But how the real one? Yeah. Unfortunately, yeah, in the real transformer, we can't make the power conserve. So the power actually will not conserve. Yeah. So because the power doesn't conserve, so we will have the value of efficiency. Efficiency. Sorry. Okay, efficiency, which symbolized by eta. This is eta. Yeah, we can say as eta. Okay, so eta will be equal to Ps divided by Pp. Yeah, we hope that the power dissipated on the secondary coil will be the same as the input one. Yeah, and as we know, the Ps is equal to Ps is equal to Vsis, and Pp is equal to Vpip. Yeah, so this all. Okay, this is for the explanation first on the introduction about transformer.